Okay, welcome also from my side. I think you have heard about my name and the title. Today I would like really to bring some content to this discussion about 5G. And one of the things we really talk about is tactile internet. And how can you realize the tactile internet? One of the things is really the Agile cloud. And I will guide you through some of the ideas we have. Of course, 30 minutes is by far not enough to explain the whole context. So if you are more interested in it, you have to follow us on the websites or joining us in our summer and winter schools in Dresden. So if we talk about 5G, and I know that you have heard a lot of parameters and technical details about 5G, one way really to describe the disruptive change is that we currently have something like 7 billion mobile devices out there. When we think about 2G, 3G and 4G, okay, 7 billion. When we go to 5G, what will happen is we will have more or less 500 billion devices. So that brings us to one of the questions, and that is maybe a very natural question. Okay, how can we bring the throughput up, right? Because we were trained as engineers to think about throughput for 2G, for 3G and 4G. So maybe throughput is the game again for 5G. And then if you look at Gerhard Fettweil's nice picture with the data rate over the years, what was his prediction in wireless LAN and what was it in the cellular, and what did really happen? Actually, you know what? Just wait. It's evolution, right? So throughput, okay, we know the drill, we know how to go up here, and this will somehow, I mean, we followed the path, why shouldn't this change? But if we come back to this question about the change from 7 billion devices to 500 billion devices, what is really different is not only the throughput, there's a little bit more than that, right? And that is really the tactile internet. So the tactile internet will open up a new area of use cases that we can look at. So without going into detail, I just depict here some of the use cases, and we can go there now step by step. But I think throughout the last year in the 5G community, more or less people have agreed that yes, these are more or less the use cases. For example, Industry 4.0, humanoid robots, something I will tell you later. For e-health, yeah, smart grids, very important. Transportation, e-learning, or even customized closing, what you see here, the selling process as such. So if you look at these use cases, they have to deal with throughput, yes, but of course this tactile internet, which means bringing down the latency dramatically, has to deal with all of these things, right? I mean, for the robots, it's clear. If you have a remote-controlled robot in Fukushima, of course, you don't want to have these old-fashioned robots with wheels because they cannot go up the stairs, they cannot do some stuff that you would do as a human being. But what you don't want to have is a long delay. So delay matters here. Also here, if you have a remote-controlled robot bringing around the elderly people, you need also some feedback, and this feedback has to become very quick. And if you talk about feedback that is really tactile, and if you talk about these two cases alone, control issues and so on, the delay has to go down to 1 millisecond. That is the dramatic change, that our latency has to go down from 50 milliseconds that we have nowadays, really down to 1 millisecond. And this you can go on if you have transportation, remote controlled cars. Yeah, of course you need this 1 millisecond to make sure that there are no accidents. You have to react. Having smart grids and combining distributed energy generations, you need 1 millisecond to do that, and so on and so on. So the real question is, how can we get 1 millisecond delay? And there have been some talks about this, about the use cases. I will more focus, how can we really do that? One of the things we have done currently is in the 5G lab, we have here two things. One is the haptical glove. So you get a glove in your virtual world, you can touch object, and the glove, by a little bit of resistance in the glove, will, when you see a ball and you touch the ball, it can be very soft or very hard. So this is something that we can now already mimic the e-health scenarios with the robots here, with the industry stuff. And what you see here is a normal Oculus goggle that we can put on, and in front of them there are very normal cameras. So what we can do now is give you the real feedback, the real information from the camera directly to the goggles, and then we just throw a ball to you, right? And then we increase slightly the delay just to tell the people how sensitive are we to the delay. And if you have a delay of 100 milliseconds, you will not be able to catch the ball anymore. You see it. Some people then try to hear the ball, right? Because they know that this is more reliable than what they see. But it's very interesting how people react on the delay and how much of the delay should be there. And of course, the more we can reduce the delay, the better it is. Some of these things you can see if you visit us in Dresden. So if we then talk about 5G, what is the real difference is 4G was about content, dissemination and communications. 5G has to cover these things because 4G and before will be part of 5G, but the real differentiator is really the steering and the control and the communication. So we want to steer and control that, for example, a car, things in your home and whatsoever, and that gives us a lot of these use cases, as we have just seen it before, but we also have a lot of these massive requirements. So if you see what we are doing today, and when we go to the 5G tactile internet world, the massive throughput, we have seen that, right? Maybe it's more evolution process, maybe we can do something in cleverly combining networks. The massive low delay, I have already told you that we need this to enable these use cases, but there are 4 more of these requirements that are coming from the low latency, but also from the tactile internet requirements, which is that we have to deal with massive sensing around us, right? You have 10K of devices around you that you have to do something with that. And because you have massive sensing and massive number of devices, maybe the whole understanding how we build networks, which means cellular networks, is maybe a dead-end street. Maybe we have cellular networks as an overlay, but for sure what will have a more dominant role there is mesh networks in the small, but also in the bigger scale networks. Then, of course, if you want to steer and control, resilience is important. You cannot claim you are controlling a BMW with 250 kilometers per hour on the highway, and then you lose control for 2 minutes, right? So resilience is very important. Safety and security as well, because you don't want other people to take over the control. And what we also have to do, it's not so much part of this talk, but we have to deal with a massive fractal heterogeneity. So nowadays you think the market is fragmented by Android. That is true. If you make an Android application, you have to support 250 different Android versions, which is dramatic. But if we think about IoT, if you think about what is coming in 5G, you will have very small devices that don't even have a battery. And then you have, in the other end, you have cars that have a big battery, big displays, totally different. So how can we bring them together? So here today you have heard about discussions about coding and air interfaces. They will be all look different. And how to bring this together in a holistic view, it's very tricky. You have to find the right answer to that. Good. I'm personally more interested in communication networks. And if you understand where we want to go in 5G, it's very good to understand the past a little bit. This is the good old circuit switch networks. These are the telephone lines, right? So what they did is they had 2 telephones for each of the speakers, and they built a physical in the beginning, but later a circuit switched or a circuit between these devices. And what you had then was as a service voice, right? And at that time, very interesting, what you really had is a connection for places. Okay. Now that looked in the beginning like this. Before you had circuit switched, you had really fully meshed, then a centralized server, so to speak, and then you really had distributed switching capabilities in the network. In the next, and this was in the 60s when Paul Barron and others discussed, we need something else. We don't want the circuit, we want to have a flow of packets. The advantage was that they were really looking at resilience at that time. If you will lose a node in this circuit, you really have to rebuild the whole circuit again from the scratch. While if you have a packet switch network, a node goes down, you can just take another route, everything will be fine. So they did 2 things. They disrupted the circuit with a flow of packets, and they really made sure that all of the nodes have more or less the same duty, the same task. And what they enabled in the end was our internet. So we are now speaking about voice and data, and we are connecting people. If you remember this company, that name in Finland, Nokia, they had exactly this sentence saying, connecting people. And now I told you all about these different use cases, the different technical requirements. So if you put this into the old packet switch, in this packet switch network, The question is, can you really do that? And the answer is, of course, no. It's very tough to do that, because if they would be able to have 1 millisecond, we would have already done that, right? So we could not do this with this, or it's hard to do it with that. Some of this stuff maybe we can mimic already now, but we need something different. And what you will see now is a network that looks a little bit different like this, and it should look like this. And what you see is a totally different kind of network that is now not only using a single pass, what we currently have in the network. Single pass is not very good. It's good for hackers, because hackers know which path your data goes. Single cloud is good because they know where your data is. They can attack you there. So for hackers, this architecture is good. What we want to have is a network where we can use all of the possible passes. A brain would do that. Ants would do that. Only stupid humans say single pass. And if you read the original description of this network by Paul Barron, 1962, he did not say, let's use a single path. He said, let's use all the possible passes from one source to the destination. But they could not realize it. It's very tricky to do that. And currently in IETF, you have multi-pass TCP. They're trying to put up 2 passes, one over LTE, one over Wi-Fi. It's really creepy to see what they try to maybe get a little bit delta out of this architecture. So the new architecture will look a little bit like this. So we will use multi-pass. Why is multi-pass good? Increased throughput, reliability, of course. I mean, if you lose one pass but you still have the others, n-1, that's good. And it's also good for security, because if you send data in a coded version, and coding becomes more important, as you will see later, over different channels, the attacker has to overhear all of the possible channels. What you also see is something like the cloud is not at the edge anymore. It's somewhere in the network. And what you will also see later, it has to move. Right? So it's not a static installment of cloud services. And by cloud, I don't mean holiday pictures only. I mean controlling functionality in the clouds that can move around. And what you see is these are, so to speak, colored graphs, right? And what we are doing here is we will use a new form of coding called network coding that is not driven end to end. It allows you coding within the network. And just looking ahead a little bit, what it really does, it even if you encode and decode in the different nodes here, within the network, every node can decide to say, you know what, I do a little bit more of coding, and they call it recoding. So every node, even without having the full information, can already, starting with 2 packets, starting to recode within the network. And what you do here is you really enable now voice, data, and control, and we are talking here about things. Okay, that's a nice evolution step, right? 3 things. And what is really nice is the first revolution here, when they were introducing the packet switch, that was seen as a revolution. It was really tough to explain the others that have a running system that makes money that we have to change. I'm now at this stage explaining the others we have to move over. When we explained this to the inventors of the internet, they bought it right away. They knew why we need this, because they could not do what was written in the original document of Paul Barron. Okay, so the next thing, when we are talking about coding for storage, for transportation, we want to have only one code. We don't want to have one code for the transportation on wireless, and one code for transportation in the wired, and one for the storage of small devices, and so on. What we want to have is one code rules them all, and this is our network code. And we can prove even that this works out, right? So this is my precious. My personal work on this was really, or let's say the biggest impact is by introducing a software library called Kodo that really can do this kind of coding. So if you nowadays want to implement something on Windows Mobile, on Android, on iOS, on Raspberries, on any device, and you want to use network coding, no problem. There are people telling you network coding is too complex. We are beating currently Intel on with their ESA L library, and they just do Reed-Solomon, which is end-to-end with a static codebook. And we have a more versatile code here. What you can do then is also to exploit hardware and multi-core support. You can use this in the native language with the C++, but if you really would like to build some stuff You can use also the language C, Java, JavaScript, and now even Python. So in Dresden now, we ordered 300 Raspberry Pis, and what we will do is we teach our students just to do network coding, building mesh systems with that. Cheap solution, right? Out of the box, works. This is a little bit of the coding speed. You can look at this later. It tells a little bit about Codo for different coding settings against Israel, which is Intel, and there are other libraries. They all do Reed-Solomon. That is what we can provide, and the first value is always encoding, and the other one is decoding. And speed is not our selling point here. What we are doing is really the kind of code that is so new. So this is one of the possible setups, wireless mesh. These are the Raspberry Pis. Here are some dongles, and you can just do something with that. So how can network coding help you how can network coding help you with that? So first of all, if you want to implement it, that is the full code for the process in Python. And I left in all the comments so that you can read it, right? So it's a simple explaining how many symbols, how big are your packets. And then he said, this is the setup. You have an encoder, a recoder, and a decoder. And then you say, hey, packet, please, encoder, give me one encoded packet. And then we give the decoder 1, which is here. We will give the packet, and then we will say packet to the decoder 1, recode it, give it back, and then we give it to decoder 2. So it's not really sending here now, it's one simulating step, but you can just do it. I mean, this is what we teach our students in 45 minutes, and they can repeat this, make their own plots. Python is very powerful to really learn something about that, right? So then what you can also do is more sophisticated setups, and this is one example to explain you why this network code is so important. So you do a simple setup. You have here a source, here a destination. The source has 64 packets. The destination wants to get this 64 packets. And then you have different links from the source to the destination. One is directly, where you lose 80% of your packets. And then if you go to the relays, you have 2 relays. Here you will lose 40%, here 40, and here 60, and here 60. Now, if you think, oh, these are very high loss rates, this is Wi-Fi, what you get in Wi-Fi. When you do measurements and you switch off the retransmission, that is what you get. I'm not a great fan of retransmissions because it's just a repetition code. It's stupid, right? We do it because we think point-to-point is the answer. Point-to-point is rubbish, is so from the 50s, right? So this is MASH. And now you say the source will take the 64 packets and it will do an encoding. And you can take Reed-Solomon, you can take Raptor, you can take LT, no problem. When you have that, you can just take these packets and send out. And if you have a Raptor or even RLNC, you have a rateless code and you just would send. And of course the relays could now help you, and there are 2 activities they can do. They can say, okay, whatever I hear, I forward. Or they can say, whatever I hear, I will recode. But then you need network coding. Then Raptor and LT are out of the question. That is a different feature. So what you see here is then the inverse density function of the number of packets that the source has to inject into the network until D will say, I have it all. And because this is hard to read, these are the mean values, right? So if you tell the people, the relays, just forward what you have, store and forward. That's the most stupid way, but this is how we do it today. This is how packet switching works, right? So they will get already encoded packets, but they will just forward it. And then you need around 100 packets from the source to the destination. If you then just enable recoding, you go down to 76. And this recoding happens without the relays talking to each other. There's no coordination between those things, so no signaling between the relays. And this makes it very powerful, right? So the recoding is some of the things that works pretty well with that. And the other thing that is, when we go away from the mesh, it's really the cloud evolution. And that will tell you a little bit about where do I get the 1 millisecond out, right? So currently where we have a robot that has a very long communication line to the cloud. Let's say this is the Amazon cloud, this is your robot. And if this is the Amazon cloud in the US and you are still in Bremen, you know the distance, you know speed of light, and you know your delay. It's not 1 millisecond. So what you have to do is you have to move this cloud closer to the robot. Okay? Proximity is the key. What we did before that was something else. We said, okay, we could keep the cloud wherever it is, in the US, in Asia, in Africa, in Europe, but we distribute the clouds, right? This is a distributed approach. This we can do today very easily over the top. And we will see also here a gain in speed. But this speed is more for large files, not for control. For control, we have to bring them down. The problem is, if you even bring the cloud closer to the user, this goddamn user might move around, so the cloud has to move with the user. And this is very tough to have a single entity to move around because you don't know where he's going. So even if it's a car and you know the navigation system tells him he should go right, but then he turns left. So you cannot prepare another instance of the cloud already for turning. You need a little bit more. So what you will see later is a distributed agile cloud. Okay? So what we have done together with this Kodo library that you have seen beginning is just to say, let's implement this distributed cloud first. And they did some kind of Dropbox where you have 4 different clouds. And one is Dropbox, one is SkyDrive, Google Drive, and Box. And now you have data. And what you do is you take the data, you encode the data, and you push it into the clouds. That's the same idea now behind multipath. It's multi-cloud. And if you do that, the first thing what people love, because these leechers, the people that really like free software, they like to also have free storage. They have a little bit free here, a little bit free, and they just want to accumulate this as one virtual drive. That is done by the code. Nice. The other thing is the data is now coded into the different clouds. And if you give 25% here, 25 here, 25 here, and 25 here, then you will see, even if Dropbox normally get hacked every 6 months, you can be very calm because nobody who will see 25% of a coded signal can decode it. That is mathematical impossible if your code is not sparse, but then we are talking about compressed sensing. But let's assume real data, right? It's very tough. A real attacker has to attack all 4 clouds. So what is the problem? NSA is in all of these 4 clouds. So what we can do is an extra level of security in our network codes that is highly efficient compared to encryption, right? But that is a different story. Now you just can push data in. The question is how much data you really want to push there. 25 was the minimum that you have to push because you need 100%. But if you lose one of the clouds, and maybe Dropbox get pissed because you're against their regulation, what will happen? They kick you out, and then you cannot decode. So the next level is to say I have 34% of coded data in each of the cloud, then I can tolerate 1 loss. Or I give everybody 50%, right? In a normal system, in a distributed system like Hadoop, the repetition factor is 3. So normally what you have, if you have one, the 100% will be copied twice somewhere else just to be sure for the resilience. Here we do it in a coded way and we can go down this 300% significantly. The other thing is, and this is what we learned later, is when you try to retrieve data from the clouds behave differently. They look a little bit like a wireless channel. Which means is sometimes you get a lot of data from cloud A. This is the time when you pull out of 4 different clouds. And sometimes you see different clouds behave differently. Here, he responds very fast, but only contributes with 4 packets. This comes a little bit later, but contributes with 8 packets, and so on. And if we try this 1 minute later, this plot looks different. So you will not know that cloud A is always the better one and C is then the second best. That change over the time. And if you then say, okay, how much data should I then push into the clouds? So here we have 5 clouds and we have 32 coded elements. And you can of course give every cloud 32 elements. This would be just repetition with a factor of 5. Or you can go down and say a little bit less. And then you see the download time for your, it was in this case 16 megabyte files. And what you see is this is distributed but not coded, and this is distributed and coded. So you get a gain by distributing the data, but you get even a bigger gain if you also code it. But what is even more interesting is the variance in the plots, where in the coded version it's very small, and here it's very big. Why is this? Because if you schedule and you plan something and it goes horribly wrong, you're here. And sometimes when you schedule, and you can be equally good as the coded, but the coded is more or less always good, right? Okay, and this variance here comes not from the scheduling, it really comes from the performance of the clouds. The more clouds you can put here, the better, the smaller the variance will become. Good. So the next level, this is just distributed, right? We are moving now from the robots. First was single cloud, now was distributed. Now we want to have the agile cloud. How does it look? So here you see a network, and here you see cloud. The big cloud tries to generate smaller version of the clouds closer to the user. And the user is moving, and we have to make sure that we have hierarchical clouds that are able to always bring best possible to the last hop, so access point or base station, following the user, right? So if we do that, that is not only that we have a clever way to distribute the data, we have to maintain the data. You can think about clouds, there opens a new cloud, you have to ask to all the others, let's fill this up, right? And how can you fill it up? You can think about, you have an uncoded system, or you have Reed-Solomon, or you have network coding. And what you see now is some kind of simulation that shows when time processes, and there are some dynamics in this setup of the clouds, you want to see the reliability of your data, so data integrity. It looks like an ice cube, and what you see is with the time the ice cube is melting, depending how much extra storage you are willing to pay for, or how much traffic. Most people don't understand that traffic costs money. If you go to Amazon and you pay cloud storage, you pay for the storage itself, but also the traffic that is lying there. And this ice cube is now, depending on the time, melting. And what you see now, if you have no coding and this guy is moving around and we have to look at into the data integrity, ice cube is melting like hell. Reed-Solomon is a little bit better. It shows that if you pay a lot in storage, you can hold it for a very long time. But even after 100 times of changes in the network, so to speak, it also will melt down. While network coding here has always the same, you can wait also 1 million of steps. It will look like this. In the end, it's not moving anymore. But you get this kind of curve that also has be shown theoretically, where you have two optimal points and even a trade-off between them, right? Here's the optimal point for a lowest possible storage with a lot of traffic, and here's a little traffic with more storage that you have to pay. Of course, there is this curve, this trade-off between them. You can play around with that. But you see, this code is very good responding to the dynamics. Now it's restarting. I was talking too long. The next thing is, where you can use it when you talk about storage is, and I have heard some talks today also about software-defined networks, right? What is software-defined networks? Is just replacing the same old routers, static routers, with a more flexible approach, right? So that opens the door for our network code to jump into that. And some of my PhD students, what they have done is they took OpenFlow, which is the realization of software-defined networks, and just enabled them to do network coding, or use this Codo library inside that. And there are two things what we can currently do. One is a real testbed, where we have 60 PCs with FPGA cards, and now luckily also some NEC routers in that, where we can really test it in a real testbed. And we have a virtual testbed that allows us to simulate up to 1,000 nodes, where we really can run real applications on top of that, and understanding what's the impact in an SDN network if we bring network coding to it. Now, I brought you a very little example here where you really see why is this so important. So when we talk about a multi-hop system, that could be wirelessly or even wired, and what you have here is the source, the encoder, so to speak, sends some packets to the relay, and to the destination. Now, if you want to make reliable communication, what you have to do, you want to have a certain amount of packets arriving here, and you know that on each of the links there are some losses. And in end-to-end, you have to put all of the redundancy needed for all additional links already into the first link. So this link carries the redundancy for the second and the third link, and so on. And then you can live with the losses until you have enough. And you hope that your estimation here was good enough, right? So you can calculate then the number of packets you need for that. You can even look at the delay for that. And then you can do the other thing where you say, okay, I don't want to put too much effort into that. Now I do an hop-by-hop approach where I do encoding, decoding. Once this is fully done, I do another encoding, decoding, and so on. So I have the optimal coding gain per hop, right? This is also still store and forward that you can do with Reed-Solomon. Okay? What will network coding do is you just encode the data, you send it out. Whenever you get something, you can send more and more data out. So every node can do it on the fly. And if you then compare these things, and this is not the analytical comparison, you could also do that. This is really a measurement that we have done in our SDN testbed. Here you see the latency gain, where you have end-to-end latency divided by the RLNC latency. That gives you the gain. And you see the number of hops and the number of losses per link, right? And then you see here are gains, right, between, here is more or less nothing because you don't have losses, then it's okay. But it goes up to 16 when you have very binary channel with a large number of hops. And the same here, if you have hop by hop compared to RLNC, also here you have gains up to 6 when you have, here you get it when there are low losses, but the number of hops are increasing with this direction. So there is a humongous gain in this kind of recoding at every node if we talk about delay and latency. Okay, and then something where our network codes will be placed in the end. It's not only these different clouds, right? It will be also in the possible mesh, wireless mesh from the network perspective in our IoT networks, in also, let's say, multi-hop and distributed devices. What you always see is this kind of cloud that will be maintained within the network, sometimes even pushed to the users. Okay? Okay, some of the ideas you have in our latest book, Mobile Clouds, with Markus Katz from Ulu. There is something about the network coding and the storage already in there. So thank you very much.
It was a very interesting talk. We have time for one or two questions. Yeah.
One question on network coding. If you apply the network coding at the application level, do you consider also lower level and higher level?
No, in the SDN testbed, it is not application layer. There it's really IP layer. In the storage, what we showed you over the top, it's really application layer. And what is in the end, what you see if you understand all the ISO-OSI tracks, where to put it, you can put it in any layer. So you can do it on physical layer, link level, IP, transport is a very interesting field, where you see a lot of gains combining network codes with TCP, because normally we know this since decades, that a code like Reed-Solomon, which is, for example, as a block code, will destroy the TCP timers. And here, because the code can work on the fly, you don't have blocks anymore. It can just spit out with a sliding window packets anytime, and it has a good impact for TCP. And application I've shown you over the top. So it's not really determined where you have to do it. You can do it all over the places.
Where you can measure gains? I mean, in the lower gains?
No, that depends on the scenario, right? And interestingly, you get even more gains if you put it at different layers. So there's a paper by MIT showing if you do it on transport and on link level at the same time, it's not a combination of both, you get more out of it. So it's a cooperative game, 1 + 1 is more than 2, right? So that is something where we are not totally sure. We cannot give you an answer, right? How much is it, right? People always like to answer, I have this setup, it depends. Because it's coding, and if you, for example, if you have a wireless mesh, no losses, you will not use coding, right? Because why you want to use coding? It will only increase your complexity. But if you have losses, then it depends where are the losses, when do they happen, and that gives you the gain. Yeah.
Because I'm wondering if, in order to reduce the latency from
Yeah.
the access, this could be an alternative to or complementary solution to the retransmission that we have.
Yes. That is what we're currently doing, right? If you have a Raspberry Pi and we put Wi-Fi on top of that, then we don't change the Wi-Fi protocol. But there is huge potential if you open the box of Pandora and telling the engineers of IEEE 8.11 that is crap what you have there. Okay? It's really crap. They have the access scheme is wrong, the retransmission is wrong, because what they do is they're very conservative. They think about point to point. They will choose the coding modulation in a way that we both have more or less an optimal thing, and the upper layers will not complain too much. That is what their goal is. But if I'm sending to 2 relays, losing 50% to 2 relays is not a problem. It's like an ideal channel. I can send quicker, right? So I need more flexibility in that. And what we have done, for example, we have built our own hardware just to understand what is the gain possibly achieved if you work on the Mac. And if you have a wireless mesh system, coding is so important, because what we have shown, for example, who should get access to the channel? If one node can combine 10 packets together, he should get 10 times more access probability than the others transmitting a single packet. Because potentially he has an impact factor with 1 packet by a factor of 10. Because you have a linear combination. If we in the room, everybody is missing 1 packet, we are 30 people, and we are missing different packets. In an old retransmission way, I say, okay, packet 1, packet 2, packet 3. And if I know that we all have, let's say, 100 packets and we all lose different packets, I make a linear combination. 1 packet, and everybody will be satisfied with that. Right? This is a very simple example to understand where the coding gain comes from. It really depends. If you all lose the same packet, I make 1 broadcast, I'm equally efficient. And this gives you also the relationship to the scenario. But often it's like this, that you have lost different packets and then you get a gain.
So the question I have is, if you look at network coding, a few years back it was a hype and everybody was talking about it, and everybody was expecting that it would be really implemented and deployed in a short while, and now some years afterwards, I think that the potential gain is clearly there, but the crappy retransmissions of wireless LAN still are being used, and network coding has not been used so much. That
would not be the conclusion. I would agree that in the beginning there's a hype, right? And it's in all of these things, people will use it to get funding from the EU for national, and then with network coding it happens something. There are 2 ways of doing network coding. The one is random linear network codes. This is the sophisticated one. The other one is a simple XOR, for people that know what I mean, right? The intra versus intra-session coding. And this one coding was very easy. Everybody understood it. There are 99% of the papers out there are about this easy way of coding. But then you run into a deadlock because they are not flexible, they are not versatile, and you don't see so much gains in that. That is a tricky part. The other codes were very complicated, and a lot of people had really problems to implement them in a way that they are not so slow, because the initial implementation were so slow that the people could not really use them. And this is really the impact of Kodo, where you can say complexity is not an issue anymore. And the other thing is, with Wi-Fi, we are using Wi-Fi mesh with network coding, we're getting gains out of it. I just want to say there's even more gain once you could open the box again. So if somebody is building up a 5G mesh system, we would know how to do it. We would make it a little bit different than it is now.
Okay. So very, very quick last question from Armin, and we move on to the next presentation.
So did I get it right when you discussed the storage problem with these different kind of clouds, Dropbox, SkyDrive, whatever these kinds of things called? So the idea of doing network coding there is that you have some information to be stored and you linearly combine the kind of information and partly store there.
Yes.
So but with network coding you do not require any kind of signal structure on the data you like to store. Right? So it's general valid, I guess, right? So if you have some special structure in the signal you're going to store, then better to do for something else regarding network coding?
No, I think in the
kind of structure in a better way.
No, the thing is, if you just see the pushing data into distributed stuff, you can use, first of all, any linear code. Even Reed-Solomon would be okay. It starts when when you want to shift data around the clouds. So we have some follow-up papers where we really show if one cloud wants to help the other with more redundancy, how can he do it, right? And in a Reed, just to understand the difference, a Reed-Solomon code, to tell something to the neighbor, needs to ask all the other people you have to accumulate everybody to tell them something. So the NSA is just faking an empty box, a honeypot. You want to help him, and everybody will come and they know where the sources are. Network coding would not reveal the sources. Network coding would say a subset of our sources will meet, recode data, put it there. But they're not everybody. And if the NSA could shut down these ones, the others are still alive. Right? It's a very tricky system. And there are a lot of people that are now using network coding for BitTorrent clients, because they know they are so flexible. You don't need a centralized station helping you. And there's a lot of potential in that peer-to-peer as well.
So thanks very much. Thank you.